This is a tutorial on functions. A function is just a special type of mathematical relationship. So when we talk about mathematical relationships, we're talking about a relationship between two sets of data. Say I had a farm with several apple trees on it. The number of apples I would harvest off of my farm depends on the number of trees I have on my farm. If I have more trees, I'm going to harvest more apples. If I have less trees, I'm going to harvest less apples. So there is a relationship between the number of apple trees and the number of apples that we're going to harvest. Another relationship would be the relationship to getting good test scores versus getting good grades. Or you can say getting good grades depends on good test scores. If I get good test scores, that will correspond to getting good grades. Now typically, when we have a relationship in mathematics, we take this number of apple trees and these number of apples, or our test scores and our grades, and we represent them with two variables, and typically we use x and y. X usually corresponds with a y value, or y depends on our value of x. Now there's many different ways to show a relationship or a relation in mathematics. We can use ordered pairs, mapping diagrams, graphs, or equations. Now an ordered pair is just a pair of two sets of data. If you've ever dealt with an x, y coordinate, you've dealt with an ordered pair. This is our input value, and then our y value has a relationship with this x value. Here are a set of ordered pairs, 87b, 79c, 64d, 99a, and 22f. These ordered pairs might represent the relationship between test scores and the grades you get in a class. If you have an 87 on your test, you'd probably get a B. 79, get a C. 64, get a D, and so on. These ordered pairs show a relationship between the two sets of data, the score and the grade. Another way to show a relationship is to use a mapping diagram. Here we have a mapping diagram, and our two sets of data are a person's name and their height. John corresponds with being 6 foot 5 inches. So John is 6 foot 5 inches tall. Jason and Jim are both 5'11", and Jerry is 6 feet tall. We can read this mapping diagram. You can think of this first box as the x variable and the second box as the y variable. And then these arrows point to which y value each x value corresponds with, or who has what height. Another way to show a relationship is to use a graph. Here, this blue line shows our relationship. For every x value we have, we end up with some y value. For each different x value, we end up with some different y value. So this graph shows our relationship. And the last way to show a relationship is to use an equation. Y is equal to 4x minus 7 is an example. Y corresponds to some value of x. If I have a value of x, well, I just multiply it by 4 and then subtract 7, and I get the y value that corresponds with that particular value of x. Now, a function is a special type of relationship where you have only one input value which corresponds to only one output value. Another way of thinking of this is for every value of x that we can come up with, we should get only one value of y. Let's look at this first mapping diagram here. Our input value is some person's name. The output value is where that person lives. Susie lives in Uptown, Jenny and Laura live in Downtown, and Kim lives in the suburbs. This illustrates a function because every single value that we input, or every x value we get, corresponds or points to only one address or only one y value. Another way to think of this is if I asked you where Susie lived, you would tell me Uptown. Susie doesn't live in more than one place. So since there's only one answer to where Susie lives, and only one answer to where Jenny and Laura and Kim live, this represents a function. Now let's look at the next mapping diagram. Here we have name and phone numbers. We have Susie's phone number, Jenny's phone number, Laura's 2 phone numbers, and then Kim's phone number. This is not a function. If I asked you what Laura's phone number is, you would have to give me 2 different answers. We have 2 y values for 1 x value, which makes this not a function. Now up here, Jenny and Laura lived in the same place, but this was still a function because Jenny and Laura were our input values, and each individual input value or each individual x value corresponded with only one y value or one output value. It's okay that they both corresponded to the same one. Each x can have only one y. So Laura having 2 phone numbers makes this not a function because Laura is the x value and the phone numbers are the y. Now let's look at these ordered pairs we're given. We have ordered pair 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. This represents a function. For every x value, I have only one y value. 5 goes with 6, 7 goes with 8, and so on. Now let's look at our second set of ordered pairs. 1, 4, 2, 3, 3, 4, 3, 1, and 4, 5. It's okay that 1 corresponds with 4 and 3 corresponds with 4. What's not okay is that 3 corresponds with 4 and 3 goes with 1. Remember, think of these ordered pairs as x, y coordinates. If the x value of 3 gets us the y value of 4 and 1, that means I have 2 y values for the same x, which makes this not a function. So now that we know what a function is, let's talk about function notation. Function notation here is this f of x. And typically when you have an equation, y is equal to a bunch of numbers involving x, you can just say that y is equal to f of x. Y is a function of x. Y depends on x. And that function we just illustrate with this f followed by x in parentheses. Now a function, say y is equal to 3x plus 4, you could also say that the function of x is equal to 3x plus 4. We're going to put some value of x into our function. Our function is going to do whatever our function does to it. In this case, our function is going to multiply our value of x by 3 and then add 4. And then we're going to get some function value for that x value. Or you can think of this as we're going to get some y value. This value of x that we plug into our function, we call that the independent variable. the f of x value, or the function value, or the y value, whatever you want to call it, we call that the dependent variable. Our function variable depends on what value we plug in for x. That's why we call it the dependent variable, because it depends on what x is equal to. Now, we don't always use f of x to show a function or to write in function notation. Sometimes it's g of x, it could be y of x. And you don't have to use x either. You could use g of t, f of z. This just means that z would be our independent variable, and then f of z, or the function value for whatever z is equal to, is our dependent variable. So let's talk about how we find that dependent variable. Let's talk about evaluating functions. Here I have the function f of x is equal to 3x minus 4. This means that I have some function and it has the variable x in that function. My function is to take that value of x, multiply it by 3, and then subtract 4. Now, if I want my function value, or f of 3, this just means that x is equal to 3. So if I want the function value at 3, all I do is take this function, 3x minus 4, and plug in 3 where there's an x. There used to be an x here. Now there's a 3. So everywhere that there's an x here, put a 3. So f of 3 is just equal to 3 times 3 minus 4. Now 3 times 3 is 9, subtract 4 and you get 5. So our function value when x is 3 is equal to 5. Or you could say f of 3 is equal to 5. Or f of x when x is 3 is equal to 5. Now sometimes they'll ask you to plug in different variables into your function. Remember, if your function f of x is equal to 3x minus 4 and they want the function of x plus a, all you do is take x plus a and plug it in for x in your equation. So f of x plus a, that's equal to 3 times x plus a minus 4. All you do is plug in x plus a for x. Now, if you want to simplify this, I would distribute my 3 inside these parentheses. And I would say that f of x plus a is equal to 3x plus 3a minus 4. So my function value, or f of x, when x is equal to x plus a, then f of x is equal to 3x plus 3a minus 4. Now let's try evaluating some harder functions. Here we're told to find f of 3 plus f of 5, and our function is still 3x minus 4. Well, all you do is divide this up. First, let's find the function value when x is 3. So we're going to plug in 3 for x. So f of 3 is equal to 3 times 3 minus 4. And we know that f of 3 is equal to 5, because 3 times 3 is 9, subtract 4, and you get 5. Now let's deal with the other half of this, f of 5. F of 5, well, we just take 5 and plug it in for x. So we have 3 times 5, and then minus 4. 3 times 5 is 15, subtract 4, and you get 11, so f of 5 is equal to 11. Now what we're asked here is f of 3 plus f of 5. So we're going to take this 5 and take this 11, and we're going to add them together. F of 3 plus f of 5 is equal to 5 plus 11. Or you can say that f of 3 plus f of 5, the function value when x is 3 plus the function value when x is 5, that's equal to 16. Because 5 plus 11 is 16. Same thing happens if we want to subtract two different function values. Here I want the function of x plus a, or when x is equal to x plus a, and then I'm going to subtract our function value when x is just equal to x. So if I plug in x plus a in for x into my function, f of x plus a, that's equal to 3 times x plus a minus 4, or 3x plus 3a minus 4. And then my function value f of x, well, f of x I already know, that's 3x minus 4. That's just my function. Now if I'm going to subtract these two values, that would mean f of x plus a minus f of x would be equal to 3x plus 3a minus 4 and then minus 3x minus 4. Now I put this 3x minus 4 because I'm subtracting the entire value of f of x, which means I have to remember to subtract the 3x and subtract the negative 4. If I distribute this negative inside, this becomes negative 3x plus 4. And if I simplify this, then our function value of x plus a minus our function, that's equal to, well, 3x minus 3x will cancel, negative 4 plus 4 will cancel, and this will be left with just 3a. So that's how we evaluate functions for different values of x, or for different function values. So now let's talk about finding the domain of a function. Now typically our function uses input or independent variables, and we call that x. So if we want the domain, we want all the values of our input or our independent variable that work. Basically, you want to figure out all the values of x that give us a function value. With certain functions, there are values of x that just don't work. Let's look at our first example here. F of x is equal to x cubed minus 4. Now, if we want to find the domain of this, we're looking for x values that don't make sense, that won't give us a value of f of x. Or if this was y is equal to x cubed minus 4, you're looking for values of x that will not give you a value of y. Because if you have a value of x that does not give you a value of y, then that value of x is not in the domain of this function. Now for this particular function, there is no value of x that you can't plug in here and get a value of y. So you would say that x is equal to all real numbers, which you can represent as this funny r. Or you can say that x has the domain that goes from negative infinity to positive infinity. Now let's look at our next function. Here we have the function g, or g of x. This is equal to x squared over x squared minus 9. Now there are two typical ways that your domain would have x values that don't work, or your domain would be restricted. Those two things that you should always look for is when you have a x in the denominator, or a variable in the denominator, or if you're taking the square root of your variable. Notice that if I look at just this denominator, x squared minus 9, If I set this equal to 0, I'll get x squared is equal to 9, take the square root of both sides, and I'll get x is equal to 3 or negative 3. If I plug in 3 or negative 3 into this equation for x, then I'll end up with 3 squared over 3 squared minus 9, or negative 3 squared over negative 3 squared minus 9. What's important to realize here is this denominator here is 0. So you'd have 9 over 0. Well, you can never divide by 0. So your denominator can never equal 0. So if you wanted the domain for this function g of x, you would say that x cannot equal 3 or x cannot equal negative 3. This means that x can be any number we want it to be, except 3 or negative 3, because if I plug in 3 or negative 3, then I do not get an answer for g of x. G of x becomes undefined, because again, I'm dividing by 0. Now let's look at f of x is equal to the square root of x. Here, x has to be greater than or equal to 0. This is my domain of x. I use this domain, x is greater than or equal to 0, because if I plug in a negative number here for x, I'll be taking the square root of a negative number, which you cannot do and get a real answer for your function. So my domain of this function is that x has to be greater than or equal to 0. Now we have one more example. We have the function k, or k of x is equal to 1 over the square root of x squared minus 4. Now again, I have a denominator, so this cannot equal 0. And if you do some math, you're going to find out that x cannot equal 2 and x cannot equal negative 2. Because if it equals either of these two numbers, then my denominator is 0. I also know I cannot take the square root of a negative number, which means x squared minus 4 has to be greater than 0. So if x squared minus 4 has to be greater than 0, if you solve this, x has to be greater than 2, or x has to be less than negative 2. Now we already know it cannot equal 2 and it cannot equal negative 2, so these inequalities do not get an equal sign with them. And I would say that my domain then is that x has to be greater than 2 or x has to be less than negative 2. So if you end up with a denominator with a variable and you end up with a square root, when you want to find the domain of your function, you have to consider both the square root and the variable in your denominator. Because if either of those values does not give you a function value, then those x values are not part of the domain of x. Remember, the domain is just values of x that will give you an answer. Now sometimes when you look at word problems, or you're developing a mathematical function to represent something that happens in real life, there is a restricted domain that you may not realize. Here we're told that Sean decides to invest X amount of dollars into his bank account. Well, Sean cannot deposit negative $2. That wouldn't make any sense. So when we talk about this word problem, we would say that X has to be greater than or equal to 0. He can deposit $0. He can deposit $1 or $100. He just cannot deposit any negative dollars because, again, that doesn't make any sense. So this word problem, if it was one, would have an inherent domain. because we know that x can't be negative. Same thing happens with geometry problems. Here we're told the width of one side of a square is w. Well, that means that w has to be greater than 0. It has to be greater than 0 because you can't measure the length of the side of a square as a negative length. Being negative 2 feet wide wouldn't make any sense. So w has to be greater than 0. It's not greater than or equal to, though, because we're told that this is a square. If you had a square with side 0, well, then you wouldn't have a square at all, because you can't measure a 0 length. So we'd say that w is greater than 0. Again, this problem would have an inherent domain restriction, because you can't measure a negative length. Now the last thing we have to talk about is when we have the sum, difference, product, or quotient of two functions. If you're ever asked to find f plus g of x, this is the addition of the function f of x and g of x. Well, then just break this into the function of x plus the function g of x. Same thing works for subtraction. F minus g of x is simply equal to the function of x minus the other function of x, g of x. Same thing happens with multiplication and division. F times g of x is just equal to the function of x, or f of x, times the other function of x, g of x. If you have a division, f divided by g of x, then take your function value of x and divide it by your other function value of x, g of x. Now with this one, it's important that g of x does not equal 0. Otherwise, again, you'd be dividing by 0, and that wouldn't make any sense. So let's do some practice problems. Here we're told that f of x is equal to 3x minus 4, and g of x is equal to negative 2x. If I want to find f minus g of 4, that means I'm looking for our function value when x is 4 minus our other function value g when x is 4. To find this, I take my function f and I plug in 4, so 3 times 4 minus 4. And then I subtract my other function where I plug in 4 for x, so minus a negative 2 times 4. 3 times 4 is 12, subtract 4, and we get 8. And then we're going to subtract a negative 2 times 4, or a negative 8. 8 minus a negative 8 is equal to 16. So f minus g of 4 is equal to 16. We have one more practice problem. Here we want to find f divided by g of a. All we're going to do is plug in a into both of these functions and then divide the f function by the g function. So we have 3 times a, because a goes in for x, minus 4 over negative 2 times a, because a goes in for x. This is the same as f of a over g of a. And I can't do much simplification with this, so this is 3a minus 4 over 2a, negative. So that's how you add, subtract, multiply, and divide functions. And that completes the tutorial here on functions.